So we're going to introduce here the idea of the mole. So the mole, this is a quantity that we're going to use to help us describe some of the calculations that we're going to do. So 1 mole is defined as the number of atoms in 12 grams of carbon. This is how the scientist that discovered this was able to come up with the number by using carbon. It is transferable to everything. So a mole is a counting number. You can think of it like a dozen. A dozen represents 12. You could have 12 cookies or 12 eggs or a dozen donuts. A dozen works to describe a bunch of different things. The same way this applies to the idea of a mole. A mole is always 6.022 times 10 to the 23rd. That's what the number is. So it's a really, really, really big number. So this number was discovered by a scientist named Avogadro. Think of it differently than avocado, but it is similar. It's Avogadro. So we refer to this number as Avogadro's number. So this is a mole, this is Avogadro's number, and this is a powerful number because this number allows us to relate atomic mass unit, or AMU, to the gram. So if you think of one atom of carbon-12, would have a mass of 12.01 AMU. Avogadro was the first to figure out this relationship. So 1 mole of carbon atoms, so if you had 6.022 times 10 to the 23rd quantity of carbon atoms, they would have a mass of 12.01 grams. This is why we are now using the unit grams per mole as our unit for molar mass. So the mole has 3 separate mathematical definitions. So the first one is the 6.022 times 10 to the 23rd particles. So particles can be defined as 3 different things. It could be a formula unit, which describes ionic substances. It could be atoms, describing elements. Or it could be molecule, which describes covalence. So just cross off the or. The or's in the wrong place there. So this mole quantity allows us to do a lot of calculations. Not only can we physically figure out how many physical particles there are in a specific amount of a substance, but it also allows us to determine for gas molecules, their volume. If you think of a gas molecule, there's not a lot of gas molecules in a certain area. So we can use this calculation. 1 mole is equal to 22.4 liters. A key point here is that this is for STP, which stands for standard temperature and pressure. We haven't really talked about pressure and temperature of gases, but they can have a big impact. That's going to be something we're going to talk about in a couple of units. And then 1 mole is equal to the molar mass, which is the 3 different types of atoms or particles we've already discussed. So molar mass, this is what we calculate from the periodic table. So if you look below, this is our mole map. Right now, our mole map has 3 different parts. We have moles in the middle. We can go to particles, volume of a gas, or mass. So depending upon which part of our mole map we're going to determines the unit or the number that we're going to use. So particles to moles, we're always going to use this Avogadro's number, 6.022 times 10 to the 23rd. Moles to mass, we're going to use the molar mass. I like to call this MM on the PT, molar mass on the periodic table. Keep in mind, you're always going to have a periodic table. You don't have to memorize the molar masses, but that's where we find that conversion. And then to go from moles to volume of a gas, we use the 22.4 liters. So we're going to do some examples, and they're going to. I'm going to emphasize certain things in this example, since we're just getting started with mole conversions. So to start with, we have 4.3 grams of sodium chloride. Grams is a unit of mass. We want to go from grams of sodium chloride to moles of sodium chloride. So how do we do that? Well, what we're going to do is we're going to take a look at our mole map. So we have the mass of sodium chloride here, and we want to get to moles. So we're going to use the molar mass on the periodic table to do that. So when we say this road map, that's what I'm referring to. Where on the mole map are you going? So we're going from grams of NaCl to moles of NaCl using mm on the PT, or molar mass on the periodic table. Right now, we're doing one-step problems. Eventually, we're going to get into longer problems. We're just starting off with one step. By the time we get to the end of next unit, we can have up to 5 steps. But one step, and we're just going to talk about 1- and 2-step problems today. So, now, I am going to require you to use, I call them T-tables. These T-tables help to organize your information and are very helpful with our conversions. Okay, so we write our starting quantity in the upper left corner, and the unit that we have and the substance is going to go in the bottom. You can kind of think of this as fractions. What I'm trying to do is I'm trying to get my units to cancel out, so that's why I'm going to grams of sodium chloride on the bottom. So that's came right from here. Up top, I'm going to put moles of NaCl. Now, we already know 1 mole of NaCl is equal to the molar mass of sodium chloride, mm on the PT. So we need to calculate the mass, molar mass of sodium chloride from the periodic table. So we're going to go to our periodic table, find sodium, which is 22.99, plus chlorine, which is on the other side of the periodic table, 35.45. Remember, we're including 2 decimal places here, and that will give us 58.44 grams. So notice that's grams per mole is the unit for the molar mass, and we have both of those units here, grams and mole. So now we're able to solve. Because our number is on the bottom, we're going to divide it. So let me pull up my calculator. So we're going to take 4.3 divided by 58.44, and that gives us our answer. So this is where sig figs are important. We were given 2 sig figs in our initial number, so we need to round our answer to 2 sig figs. So this 0 right here is not significant. Remember the Atlantic and Pacific rule. If the decimal point is present, you start on the left and work your way to the right. You find your first non-zero, which is 7, and then count however many sig figs you need from there. If it's absent, you do the opposite. You start on the right and work your way to the left. So we're going to have 7,4 as our answer here. So we're going to have 0.074 moles of NaCl. In the next example, we're doing the opposite. We're given moles of NH3, which is ammonia, to grams of NH3. So the reason why we always most often use grams is because grams is something that's easy for us to measure. We can put it on the balance. We can very easily take the mass of it. So in this example, we're going to go moles of NH3 to grams of NH3. So we have moles. We're starting here, and we're headed towards the mass. So again, we're going to use mm on the PT, or the molar mass on the periodic table. So we're going to do the same thing. We're going to put our initial number with our units, moles of NH3 in the upper left part. So we're going to take our unit, moles of NH3, and put it on the bottom. The reason I'm putting this on the bottom is I want the unit to cancel out. So sometimes you're going to have moles on the top of your fraction, sometimes you're going to have moles on the bottom. It just depends on what you're starting with. Because I'm starting with moles, I have to have moles on the bottom. And then on the top we have grams of NaHCl. So something to point out here, notice in the last example, we had grams of NaCl, grams of NaCl cancel out. Now we're doing the same thing, moles of NH3, moles of NH3. They're both canceling out. Whenever we're converting units like this, we're always going to have a 1 for the mole. So now we need to take a look at our periodic table and figure out the molar mass of NH3. So you should end up with 17.04. So you're going to take 0.00563 times 17.04. And that will give you the mass of your sample. So notice we have 3 significant figures here. So our answer needs to be rounded to 3 significant figures. So we're going to have 959 grams of NH3. So if you think about this in terms of what we just did, we figured out that our sample has a mass of 0.0959 grams, which is pretty cool. In the next problem, we now have atoms of barium to moles. So we're given atoms. P.S. Don't abbreviate atoms ATM. So yes, ATM is a machine you get money out of, but it's also a unit of pressure, so you can't use that as your abbreviation either. So atoms of barium. So we're going to moles of barium. So our roadmap, we're going from atoms of barium and to moles of barium. So in a one-step problem, your roadmap's not super helpful. I understand that. Roadmaps are more helpful when we start getting into more complex problems. So we're going to take a look at our mole map. So here we have particles, which are atoms, and moles. So we're going to use Avogadro's number, or 6.022 times 10 to the 23rd. You will need to have that number memorized. Most of the 22.4, same thing. But the molar masses, you just need to know how to do it. So you could write 6.022 times 10 to the 23rd, or you could write Avogadro's number there, whatever works for you. So we're going to do the same thing. So we're starting with 3.0 times 10 to the 14th atoms of barium. So atoms of barium are going to go in the denominator, and moles of barium are going to go in the numerator. Because we're changing units, the mole is going to get 1, and atoms are going to get the Avogadro's number, 6.022 times 10 to the 23rd. So now our unit of atom is canceling out, so we'll be left with moles of barium, which is what we want. However, plugging this into your calculator is a little tricky. So we're going to take 3.0 times 10 to the 14th. You can plug it into your calculator using the E function. Notice it's a capital E. If you hit the second comma button, that gives you that E. And we're going to divide that by 6.022 second comma, which gives us the E, 23. So when we solve this, we should end up with, in this case, a very small number. Again, we'll have to watch our sig figs. We need 2 sig figs because we started with 2 sig figs. So we're going to round this to 5.0 times 10 to the negative 10th. So then this is atoms of barium. I meant moles of barium, not atoms. Sorry about that. So in the next example, we're going to go from moles of carbon dioxide gas to molecules of carbon dioxide gas. I usually use MLCS because in my mind it makes more sense as molecules. We're going to do the same sort of mole map. We're going to go from moles of CO2 to molecules of CO2. And according to our mole map, we're going to use Avogadro's number again. So 6.022 times 10 to the 23rd. Our work is going to be set up similarly. So we have 0.156 moles of carbon dioxide. Moles of carbon dioxide will go on the bottom because we want our units to cancel out. And molecules of CO2 will go on the top. So 1 mole of CO2 is equal to 6.022 times 10 to the 23rd molecules. So now in this problem we're going to multiply them together. So we're going to put 0.156 times 6.022 times 10 to the 23rd, which should give you 9.39 molecules of CO2. Okay, so I did that on purpose. I missed something. If you look on your calculator, there's a times 10 to the 22nd or an e to the 22nd that you really need to include. That's a very important part. 9.39 is helpful, but that without the times 10 to the 22nd, you're going to be way off in what your answer should be. So again, it should be 9.39 times 10 to the 22nd molecules. So this is just to show you this E22 is times 10 to the 22nd. You should write times 10 to the 22nd. You shouldn't write this E. It's a better communication tool.